Hello everyone, thank you for joining today's session on resolving high-speed PCB design challenges. I'm Vandana and I'll be one of your presenters today. So for those of you who are new here, I'll tell you a little about us. Sierra Circuits is the one-stop solution for PCB fabrication, assembly and component management services. We have a 70,000 square feet PCB manufacturing and assembly campus in Sunnyvale, California, and we offer advanced technologies like HDI, rigid flex PCBs, RF, and microwave PCBs. I'll just tell you a little about why choose Sierra Circuits. At Sierra Circuits, we have design, fabrication, and assembly all under one roof. And the seamless integration between the layout engineers and fabrication experts enables fast iterations, fewer errors, and better performance. Our dedicated design engineers will help you with real-time DFM and DFA feedback. This prevents costly rework and delays. Designing a high frequency circuit board is not a joke, and it requires precise technical knowledge and expertise in signal integrity, trace routing, and material selection. Sierra Circuit's design team is capable of addressing exactly that high speed PCB design challenges, like achieving consistent line impedance, reducing signal reflections, and managing crosstalk between adjacent traces. This will be the agenda for today, basically outlining how Sierra Circuit handles high speed design jobs. Let's start with how to choose low loss materials. While designing high speed jobs, our design engineers select materials with a DK less than 4 and DF less than 0.005. To reduce the skin effect losses at high frequency, we usually use low profile copper foils such as hyper low profile HVLP, reverse treated foil RTF, and ultra low profile. Being tied up with our in-house fab team, we understand the importance of selecting a laminate with a CTE that aligns with that of copper. We at Sierra use our PCB material selector tool to make the right decision when choosing high-speed materials. Here you'll see how our tool helps. So I'll just show a quick demo on a material selector tool. So this is a material selector tool that allows you to search and filter out the rigid and flex materials from the database that best suits your design needs. You can scroll all the way down here and click on this Go Submit button, and all the materials available in the all the rigid materials available in the data will be displayed there. Then we have all of these various categories that will help you with the material selection. The first being the material type. You can choose a flex or a rigid board. You can click on yes for a halogen-free material and on all if you want a halogen-based material as well. You can also click on this very high thermal conductivity if that's your requirement. Under electrical properties, in the speed loss section, we have a drop down here that categorizes all the materials into these categories. Let's go with high speed, low loss for now. And then we have three input parameters here. That is the maximum signal frequency content, fastest signal rise, and the highest data transfer rate. You can click on any one, you can enter any one of these parameters and the others will be automatically calculated. For example, let's go with 10 gigahertz here. When I click outside, the other two are already calculated and displayed. You can use these sliders over here to choose the range of your dielectric constant, similarly for dissipation factor and dielectric electrical strength. We have a drop down here for the CTI class and voltage. And under thermal properties, we have the glass transition temperature, decomposition temperature, CT in the XY axis and the Z axis, and of course the thermal conductivity. Under chemical properties, we have moisture absorption and an option to choose CAF resistant materials as well. In mechanical properties, we have the tensile modulus, tensile strength, and the flexorial strength. Lastly, we have a drop down for the family name, which you can choose one of these, and those materials will be provided. Similarly, we have a drop down for material manufacturer, IPC number, and the slash number. Now click on Go Submit, and all the materials that belong to the criteria that you have chosen will be displayed over here. You can click on this view button to view the data sheet of that particular material. You can also change the unit system here from imperial to metric if you wish to do so. You can click these tick boxes over here to all your desired materials and click on this compare button, and it will show side by side comparison of all the properties of these materials. We have also provided a column over here that basically states if the material is HDI preferred or not. Let's get back to the presentation now. We start with handling high frequency traces and reference plane. One of the most important thing in ensuring uniform impedance. When routing high-speed circuits, our designers thoroughly check for impedance discontinuities. We implement daisy chain routing and maintain a spacing of at least 3 Ws between traces, where W is of course the trace width. Additionally, our designers incorporate series and parallel terminating resistors at the driver and the load end respectively. I'll just give another quick demo on our impedance calculator. This is another very important tool that will help you. Here. So impedance calculator uses a 2D numerical solution of Maxwell's equations for PCB transmission lines and renders fairly accurate results. Our impedance calculator tool supports 82 different impedance models. As you can see, we have the uncoated, coated microstrip, embedded microstrip, and the strip line. And for each of these geometries, you can choose single-ended differential pair models here. I've just opened the coated microstrip over here for now. Let's enter the dielectric height, a dielectric constant, a coating height H1C, coating height H2C, and the coating dielectric constants ER2 are already entered here as a default value, but you can change that if you wish to do so. Then we have delta W, which is nothing but the distance between the top of the trace and the bottom, a difference between the top of the trace and the bottom of the trace. You can click on this help content here, which shows or displays a table that suggests delta W values based on the starting copper weight. And you can use it as a reference. Let's go with 0.5 for now. Enter trace thickness and a trace separation. Now to calculate the trace width, I will enter a target differential impedance. Let's go with 100 ohms and click on calculate W. You can also calculate the differential impedance instead by entering the trace width and clicking on calculate ZD. So you can see the other parameters are calculated and displayed here. Now we have the signal loss, S parameter, and crosstalk calculators available for this model. I'll just enter the dissipation factor of frequency. Surface roughness, let's go with 6 because that's a standard roughness for a foil. And length of 2 inches. Click on calculate loss and the signal loss output in the odd and even mode is calculated and displayed. Similarly, we have the S parameter calculator here. We enter the source impedance, the load impedance. You can use this drop down to choose your output type and click on calculate S parameters. Now, since this is a coated microstrip, we have a 4-port network, and therefore a 4-port S parameter and mixed mode S parameter matrices are displayed here along with the characteristic impedance and the propagation constant. One thing to make sure before using the S parameter calculator is that you have to use a signal loss calculator before, because the frequency that we have entered in the signal loss calculator will be used in the calculations here. Then we have the crosstalk calculator. Let's enter trace length of 2 and the signal rise time of 100 picosecond. Click on calculate crosstalk, and the near end crosstalk and the far end crosstalk results are calculated and displayed. Moving on, we have designing ground planes now. Our designers ensure a dedicated ground plane for each high-speed layer. To provide multiple low impedance return paths, we implement via stitching along the ground plane edges or high-speed traces. We also maintain the via stitching gap between lambda by 20 and lambda by 10, where lambda is the operating signal wavelength. Additionally, our designers use top and bottom ground pores in RF layouts to mitigate EMN crosstalk. While designing, we also ensure there is at least 1.5 to 2 times the trace width between an RF trace and the ground pose. Now I will pass on the screen to Abhishek. He will give you a demo on handling high frequency traces and reference plane.
Yeah, thank you. Thank you, Vandana. Yeah, so I'll just show you what we at Sierra Circuits do while designing a high-speed RF lines. So this is a board which works on a frequency of approximately 30 megahertz to 3 gigahertz. What we have done, there is a circuitry over here which is involving a lot of inductors, mostly LNAs, chokes, then filters, and there is this isolation transformer over here, which is basically separating the two grounds on the other side. And there is a band pass filter, which is then passing this signal to the SMA connectors. Now, we are designing a single-ended trace over here. This is not a coplanar structure, although there is a copper over here, but there is a 3W separation. The trace width here is right now 7.6 mils. So we have used the 3W rule, which is 22.8 mils. So the separation, that is because we are not using coplanar structure. And since we are not using coplanar structure, we are not using the shielding wires also over here. So what we do is, so initially we place the components in a manner that it will not create any stubs. For example, now as I can show you over here. Yeah. Yeah. So this component, as you can see, suppose I place it slightly down over here, then I can still connect it like this. I can still connect it like this, but the problem will be it will create this unnecessary stub, so which can result in reflections in the signals and can result in deterioration of the signal. So to avoid this, it is important that we place this properly so that those unnecessary stubs are avoided. So that is the very first thing while doing the placement, that you have to place in such a way that you do not create unnecessary stubs. That's what we do over here, and then we start with the routing. So routing, as I said, this is single-ended. If you want to use shielding wires, then definitely the rule will be lambda by 10 or lambda by 20. So generally, if you don't know your frequency range, then I would say go with 20 mil to 30 mil spacing between your wires. Now I'll just show you. Before that, we have also used a shield over here. As you can see, the one which I am highlighting, it is a physical shield which is put around the circuit. So whatever EMI radiations that is occurring over here, we are to make sure that it is not interfering with anything else outside or anything else. The noise is not interfering with this particular circuit because it involves a lot of high frequency signals. Um, so I'll just show you. So the next thing is the reference plane. So now your signal line should have complete reference planes on your adjacent layer, which is layer 2 in our case. As you can see, we have followed complete reference plane. There shouldn't be any splits in your reference planes anywhere. So make sure that all the signal have complete reference plane. So now we have also used curved angles over here. So curved angles are better in case of impedance lines generally, because 135-degree bends can create a small impedance discontinuity. So now suppose I want to route this. I'll just show you how to route it. So I'll just delete this trace and I'll route it again. So initially I'll route it with normal bends. And then I'll just select the slider option, make it arc corner, and I'll click on this and I'll simply drag it like this. So that I can make it curved. So this way you can make your traces curved while routing if you are using Allegro or Orchid. So, and we have used stitching wires. So generally to stitch all the grounds properly. So whatever noise that might be involved. So now suppose you don't have enough space for this physical shield, you can also use virtual shield with the help of wires. Again, the wire spacing would be governed by lambda by 10 or lambda by 20 rule. Yeah, thank you. Vandana, you can take over.
Yes, thank you, Abhishek. Let's now start with routing fine pitch BGAs. Sierra Circuit's PCB designers ensure optimum power integrity is preserved while routing fine pitch BGAs with limited real estate. We implement via in pad to maximize routing space and reduce parasitic capacitance. Additionally, filled and capped vias ensures flat surfaces for BGA assembly. We also use stacked microvias for efficient vertical routing through multiple layers. Microvias reduce layer count while maintaining signal quality. We have another demo by Abhishek now on routing fine pitch BGAs. Over to you, Abhishek.
Yeah, thank you. Yeah, so I'll just show you what are the different BGA sizes that we generally work with, and what are the different rules and the wire sizes that we use. Now, this is 0.8 pitch BGA. So 0.8 pitch basically means the center to center um, spacing, which is over here, 0.8 31.5 mils. And this gives us a air gap between the diagonal air gap of approximately 32.548 mils. So now, when it comes to wire selection, this is 0.8 and 1 also you can consider the same thing. In this case, 32 mils is available over here. So easily you can place a normal wire, which is 8-18 mils or 10-20 mils, whatever you feel like. So you'll have enough space on the both ends. So that shouldn't be a problem. So you don't require wire on pads, or you don't even require blind and buried wires. So you can use dog bone structure. Only thing you will have to look at the stub length of your wire. If your frequency is too high, then you might have to go for back drilling, or you might have to use the blind and buried wires just to avoid that stub length. But if that is not the case, then easily you can use a normal through wire in 0.8 pitch BGA. So here, half ounce on the external layers, copper foil should work perfectly fine. The next thing after placing all the wires is to place the capacitors on the bottom layer. So generally on the bottom side, we use all the we place all the capacitors, and we try to place it in such a way that each pad is close. Ground pad is very close to the ground pad, the ground wire, and the VCC or whatever is the voltage is closer to the voltage wire. 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 So we generally follow the grid in placement. So that is whatever is the grid, 0.8 is the grid, then we divide it by 2, then we keep the grid as 0.4 and we do the placement. So because that helps in placing the wires exactly at the center of the pads, also the capacitors can be placed exactly at the center. Now, while routing, the very first thing that we try to do is we try to use top layer as much as possible. As you can see on the edges over here, the outer rows, they are routed on the top layer. So we try to pull out as many signals on the top layer, and that reduces the number of wires that we might require in this area, because this area can block your power signals on the internal layers also. Then on the internal layers, it is simple. You just have to follow the orthogonal routing. If you are using layer 3 and layer 5 for routing, then one layer you can route all the traces on vertical and top and bottom side, and the other layer you can easily route all the traces on the left and right side. So that way you will not obstruct any signals, and you should be able to easily pull out all the traces. The width over here is quite high, which is 4.5 mils, and the clearance is 7.5 mil. So half ounce copper foil will also easily work over here. So this is 0.8 going to 0.65 So this is now a 0.65 pitch BGA. So I'll just show you how it looks like. So via if I remove and tracks the polygon. So this is how the BGA looks like right now. One advantage in this BGA is there are a lot of open spaces over here. So what we have done, we have tried to use these open spaces so that we don't have to use blind and buried wires. So wherever possible. So I'll just show it to you. Now this to here is 0.65, as you can see, which is 25.5. And the air gap is 23.191 mil. So now in this, we have the wire size that we have used is this is 818 mils, which is 5 mil annular ring. Because as you can see, there is open space in this area, so you can easily put wire over here. But suppose there was no open space, then you might have to put it over here between the two pads. In that case, you have 23 mils, so you can use 816 wire. That will leave you with 4 mils on each side, but you will have to go with quarter ounce copper foil on the external layer. So yeah, so that is one thing. Otherwise, as I said, you can also do is you can place this wires on pad directly if the space is not enough. So as you can see now, suppose this is if I move over here. So suppose now this was placed on these two pads, then you will be left with the spacing of 7.5 mil. That should be easily perfectly fine. So wire on pad is another solution. And if everything doesn't work, then you have to go with blind and buried wires. So again, the same thing we have followed. We have tried to route all the traces on the outer layer. So I'll just show you the trace fit. So here it is 5 mil, and the air gap would be here it is 3.79 mil. So which is slightly less because of the because the spacing is less in this case. But 3.79 mil or 3.8 mils, that should work perfectly fine with your quarter ounce copper foil on your external layers. So this is when it comes to the 0.65 mm pitch BGA. As you can see, internal also you can pull out traces. It is possible to pull out internal rows also on this particular BGA. Internal layers, again the same thing. As I said, orthogonal routing you'll have to follow. So that depends upon how you place your components and how you plan your routing. So coming to 0.5 mm pitch BGA. So this is slightly a different type of 0.5 mm. So here there is a combination of 0.5 and 0.6, 0.65. So the center pads, as you can see, these are 0.65 and the outer pads are all 0.5. So I'll just show you the center first. So this is now, here there's one sec, pads, tracks. So I'll just show you the air gap that is available. Here the air gap is quite high, 27 mils. So easily you can put a wire over here, which is of, right now we have used 616. So which is 60 mil is our board thickness. So 6 mil with respect to aspect ratio 10:1 should easily work fine. So there are common pads, ground. So we have put in the diagonals, we have put the wire. So that this is perfectly fine for all power section over here. Now coming to the 0.5 mm side. Right. So now over here, what we have done is we have tried to use as many through wires as possible so that the cost of the design is kept as low as possible. Uh, Only at certain places we had to use blind wires. I'll show you where. This is over here. Like for example, consider this pad, ground pad. This is the wire, blind wire, which is going from 1 to 2. Now, the problem is it is blocked from all the sides. Like this wires over here is blocking. This trace over here is blocking it, and also on the bottom side. Another thing that we try to do is we don't keep ground wires very far away from the pads. We keep it very close to the pad. So the best solution was to use a blind wire, which is right now the spacing. I'll show you the air gap. This is 0.5 mm pitch BGA. So here it is 18 mils. So 18 mils, you cannot put a through wire. So even if you use 614, that will leave you with only 2 mils on each side. So only possibility was to use a laser drill blind wire, which is 4 mil and 9 mil pad. So 4 mil is hole and 9 mil is pad, which is 2.5 mil annular ring. So, and then coming to the line widths. So as you can see over here, this is now 3.5 mil and with the spacing of 3.5 mils on each side. So that is possible with a quarter ounce foil on the external layers. Another thing you must have noticed over here is the line width over here is small initially, which is 3.5 mil, and then it increases. So generally when you are fanning out, it is okay to route with the lower line width as per whatever minimum is possible, because it will not affect your, even if it is an impedance line, it shouldn't affect that much. Then once you pull it out, then you can go with your normal impedance line width or whatever you want to follow on your normal design. So this is normal practice while doing the fan outs of a BGA. Yeah, thank you.
Thank you, Abhishek. Let's move on to designing with high-speed interfaces. We excel in designing high-speed interfaces like PCIe, DDR, USB, and Ethernet. To minimize the stubs, we incorporate a daisy chain topology for routing DDR 3, 4, 5 address and command lines. Our designers also ensure accurate terminate of flyby signals with resistors at the end of the bus. For USB 3.0 or 3.1, we route SSTX or SSRX with minimal bends and symmetrical paths to minimize signal degradation. When designing Ethernet interfaces, such as 100 base TX, 100 base T, our designers pay careful attention to the length matching of differential pairs. We have another demo on designing with high-speed interfaces. Over to you, Abhishek.
Yeah, thank you, Vandana. So here I'll show you how we generally route a differential pair. This is a USB differential pair. As you can see over here, this line. So what I'll do is I'll simply delete this for now. So before you can start routing, you need to know what is the differential pair, what is its trace width, what is the impedance of that particular trace width. So you have to do all those calculations first from your stack up, and then go to design and classes. So the very first thing that we do is we create classes. So this is differential pair class. So USP 1DX that is created over here. So we'll use this particular class, and then we go to design rules, and we create the rule for this particular differential pair. Now just show you. So first of all, this differential pair 90, this is the rule which is created for this both of these differential pairs, USB 0 and USB 1. So the line width is 4.8 mils, and the gap between the differential pair is 6.2 mils. So this have to be set first of all. This is on top layer because we are going to route it on the top layer. Then you have to set clearance rule. So for polygon, generally we follow, if you're pouring polygon on the same layer where the differential pair is there, then you'll have to follow 3W rule minimum, or you can go with 5W also. Here it is 30 mils. 4.8 is the line width, so which is quite high from what the 3W is. Even if it is higher than 5W, then that should be completely fine over here. And another rule for differential for USB is the two lines of a differential pair in a USB should be length matched, which is if you go to mesh lengths over here within differential pair, we have to length match them with a tolerance of 5 mils. So these are the important rules that you have to set before you can start routing. So once this is done, I can go to route and interactive differential pair routing. So I just route this. Right, so we have routed this differential pair now, but the job is not done because we have to now length match the two traces, which is the P and N of a differential pair. So to do that, you have to go to design route again and go to interactive line tuning and just use this sawtooth one. Um, so so what I'll do is I'll just click on this and I'll pull it this way outside. Something is wrong. Guardian. Right, so when I pull this, as you can see, now initially it is red, but once I pull it, it should become green. So once it becomes green, it means that the two lines have been length matched. So now the general spacing over here is 6.2 mils. So after you pull this, what we generally try to follow is doesn't go beyond 3s. Generally it is 2s rule, but we try to keep it between 2.5s somewhere. So the spacing after pulling, it should be not more than 3s maximum. So don't go beyond that. If it goes, then it is we recommend to use multiple such extension instead of using a single extension. So similarly, we do the routing for Ethernet lines. Also, if there is PCI lines, we create classes of Ethernet with all the TX and RX line on all the differential pairs, and we create rules for the length matching of those lines. Similarly, for PCI lines. So these are the different interfaces that generally we work with. This is just an example that we have shown you. Thank you.
Thank you, Abhishek. We usually come across a lot of PCB designs and very often have to deal with interesting and complex design jobs. So now we have selected two such case studies today, and Abhishek will be explaining them to you now.
Yeah, thank you, Vandana. Yeah, so we work with such different types of high-end high frequency projects. So one of them is this over here, which involves FPGA. So this is an FPGA of 1 mm pitch BGA over here, and there are four DDRs over here. So these are the four DDRs, 1, 2, 3, 4. This is 0.8 mm pitch BGA. So as I said, the fan out is not an issue. This is a normal dog bone structure, and the wire size I'll show you. Right, wire size is 816 mil, so that is perfectly fine. So with respect to the fan out and the wire placement, that is okay. Only one thing you have to make sure is this is DDR3, which generally, as per the customer information, it was 800 megahertz of frequency. So we had to calculate the stub length. So after placing this wire, so whatever is the length remains, that you'll have to check. If it is less than whatever the sub length is required, then it is okay. If it is not, then you might have to use either blind and bed bias, or you'll have to use back drilling for that. So that has to be kept in mind. So that is the very first thing that you have to calculate before starting the fan out. Then the placement of the component. So this is placed over here. So this DDRs are slightly kept away because as you can see, there are these holes. So there was going to be a fan mounted on this on top of this FPGA for its sync purposes. So that's why we had to keep it slightly away from this particular FPGA, but we try to keep spacing of sorry, the length of the traces after all the length matching and everything up to 2500 mils, that which the design guideline that generally we follow for all the DDR lines. So now there are four DDRs, so total there are 64 data lines, which is going from 0 to 63. So which is divided into 8 different sets. Each set of a data line consists of 11 lines, that is 8 data lines, and there is a strobe signal of a differential pair, and there is one more command signal that is generally we route in a one single set of a data set. And then there are 25 address lines in this, and along with that, there are clock signal and command and control signal like bank select signals, all those chip select. That is another 10 signals, which is making it around 34 to 35 signals. So now, how did we route this? So first of all, we had to do the placement. So on the top side, it is all the DDR. So on the bottom, we placed all the capacitors, decoupling capacitors. As I said, it is placed very close to the wires. Now, the very first thing that we noted over here was so here we used flyby topology, that is daisy chain topology, wherein one signal will go in line. Like for example, as you can see this differential pair, this is a clock signal, which is going at this particular wire first, then it is going to the next wire, then to the next wire, and to the last wire. So that is basically going from one DDR to next DDR to next DDR to next DDR. So the DDRs are placed with starting from 0 on the left hand side and till the end in increasing order to the right hand side, which is 63 over here, this side. So we had to basically identify this particular clock signal first of all, because it is going from from all the four DDRs. So we had to push this wires at the center slightly away. So as you can see, these wires are pushed away. This is necessary to identify at the beginning, which we did, because if we suppose route it, place all these wires initially fan out, and then we start routing other traces, and later on realize that this is a differential pair and there's not enough space between wires to route it later on, then you have to do the rework all over again. So that's why it is important that you route. That's why what we did was we routed the clock signal first. So and then accordingly placed all the wires. So this differential pair after this routing. Then the next thing was this now the this differential pair clock signal acts like a separation between data and ground signal. So all the data signals are on the top side of this, and on the bottom side all the ground signals are there. Uh, Coming to the routing. So now as you can see, on the bottom side we have used four layers. Sorry, not on the bottom side. So this signal 1, signal 2, which is layer 3, layer 5, then layer 12 and layer 14, we have used for routing all the traces. So that is because we have tried to use ground planes on the both side, like 11, 13 and 15. So both the signals are sandwiched between ground planes. So similarly over here, layer 3 and layer 5 are sandwiched between ground planes. So that is the normal strategy that we try to use. So while designing our stack up. So now all the address lines and the control lines are routed over here. So as you can see down, coming to the termination register placement. So initially, so now all the termination registers are placed at the very end of the decision. So now, as you can see, the decision is coming all the way like this till the end, which is on the right hand side. After that, at the end over here, as you can see on the top and bottom, we have placed all the termination registers. So these are our termination registers, this over here, and on the bottom layer, this one. So these are not 0201 sizes, but initially customer has selected large sizes, so 0603. So we had to place them over here like this wherever the space was available, because it was not fitting over here. So that due to that, some discontinuities were created in the impedances, and it was creating some distortions in the signal integrity while when the simulations were done. So then the solution was reduce it to 0201, because that is the only way we can put them very close to this wires. So that's what we did, and then they were placed over here, which is generally at the end of your decision, which is the last line in your sequence. So that resolved the problem. So this is with respect to the address lines. So then coming to your data lines, um, there are total 8 sets and we have 4 layers. So what we did, we routed 2 sets on each layer. And the way we did this was we generally try to do what is, we suppose there are 11 lines in a data sets, we route them all on a single layer. So if you are going on internal layer, for example, 3, then all the 11 signals will be routed on the layer 3 itself. That helps us with keeping all the signals in one layer so that it becomes easy for us to identify what is what. And secondly, it helps us when it comes to the via length. So whatever via length that adds up to your signal, right? Whenever you go from one layer to another layer, that remains same for all the signals in that particular data set. So the worry of something has added up to something is gone. So that is why we try to route them on single layer. Now, another strategy that we used was initially over here on the left hand side. Suppose we are using a set which is starting from 0 to 7. So 0 to 7 data lengths. We routed over here, for example, on layer 4, layer 14 is a signal 4. Then we did not start with signal 5 to 15, 8 to 15 on the same layer, because it will be very close, because it will be over here. It will start blocking our way. So then we shifted on the with a 24 data lines. So next 32 to 39 was then routed on the same layer, because we'll have enough space between the two so that we can route it easily. So that strategy we have used, and then we generally try to route while routing. We try to use spacing more than 3W, basically 5W or more, because it will leave you with more space. Because when you will do the length matching, the extensions like this, you should have more space available. So that helps us in giving more space. So these were the strategies to route this particular PCB, and it did work in first go. Um, so this is the first case study. Then coming to the next one. This is now it involves 4 BGAs over here. This actually was a quite a big board. We do not know the application because we were not told. So these are um, 4 BGAs over here. So this is a 0.4 mm pitch BGA, and these three are 0.65 mm pitch BGA. 0.65 mm pitch BGA, as I already mentioned to you over here, they have used blind and buried wires over here. So because of the spacing between the balls, so this is only 18 mils of air gap, so through wire is not possible. And this is a 95 mil pitch, 95 mil thickness PCB. So we'll have to use a 10 mil drill. So that's why for all the 0.65 mm pitch BGA, this the blind and buried wires are used in a stacked manner. Um, then uh, I'm just focusing on this particular pitch BGA, which is 0.4 mm pitch BGA. Now, this ICs we are not known. So what are this? So these are just the socket. As you can see, these are holes. So only the sockets were given to us, and all the connections were known to us. So uh, on this particular board, there were some 70 ohm impedance traces which had to be routed from this particular pitch BGA, this particular BGA to all the 3 BGAs over here. There were 3 different sets of 3 different colors. um, so they were going over here, and over here, and each set had to be length matched with a length of not more than 2,100 mils, so which was approximately 5 centimeters. That was the restriction limitation. So that was told to us we have to do that. So one problem that created was due to this um, the sockets, because now if this was a normal IC, then we could have placed it much more closer, because but there are these holes over here. So that's why we had to keep it slightly away, so that in that itself was taking about around 150 mils. So that created a problem for us, because already we were having constraint of the length, and due to this the constraint even increased. So we tried to place them as close as possible. Then coming to this, so now this is again a 16 layer PCB, which is 95 mils thickness. Okay, so I'll just show you the spacing that is available between any two pads. So now this spacing, as you can see, this is 5.9 mil air gap. So forget about routing a trace between between these two pads. So only possibility of routing is on the top layer, on the outer row. As you can see, inner rows, it is not possible to route on the top layer between the two pads. So everything has to be on internal layers, all for all the inner rows. Second thing is the spacing between the diagonal over here is over here. So now this is 12 mils. Again, 12 mils air gap through wire is not possible over here. And also this is a 95 mil board. So if you are using a complete through wire, you'll have to use a 10 mil drill, which is quite high. So that is gone. Again, a blind and buried wire is also not possible, because even if you use 4/8 blind wire, then you will be left with only 2 mils on each side. That is again very low for quarter ounce copper. So the only possibility was use wire on pad, and that too blind and buried wires. So another thing is, uh, so as you can see, all the wires are placed on pads, okay, and those are blind and buried wires. So next thing is we had used stacked wires, not staggered wires, stacked wires, because the reason is, now as you can see, this traces on inner layers. So this is layer 3, this is layer 5, so then layer 7, 9, no, sorry, this is layer 7, 9, and 11. So so many traces. So suppose, now imagine if this is layer 3, as you can see, this is now stacked wires. Even though even with that, it looks like there is not enough space for placing more wires over here. It's so many traces around. So that's why it was not possible to place staggered wires, because now suppose this was going from 1 to 5, then one we might have to use 2 different areas for placing. So you will require one more space over here. So that way, what will happen? The number of wires that is visible over here, they will double up, and that will occupy more space. So that is one reason. Another thing is, due to the space constraint, when you place the staggered wires, the hole to hole clearance should be at least 7 mils for blind and buried wires. So that was another constraint. So that's why stacked wires were used. and we had used 4 laminations. Initially, we planned 5 lamination, but due to the cost and stuff like that, we had reduced it to 4 lamination. So definitely the cost will increase because of the stacked wires and the number of laminations. Okay, so then how did we plan our wire placement? So now taking initially the power wires. So now power pads are on the top and all the capacitors are on the bottom. As you can see, all these capacitors are on the bottom. You imagine I want to go from 1 to 16. So how do I go? So now initially we had used this wire of size 610, which is 6 mil drill, and 10 mil pad, which is this is a blind wire. Now it is going from layer 1, for example, layer 1 to layer 2 over here, then layer 2 to 3, one more wire again stacked, and then 3 to 4. No, sorry, wait. So yeah, so 1 to 2, 2 to 3, and 3 to 4 also it was going. So when I will turn on 4, you will see that the pad size will increase slightly, right? So the pad size now has increased because on the layer 4, there is a buried mechanical drill, which is of 6 mil hole and 4 mil elder ring, which is 14 mil pad. So that's why we had used layer 1 to 2, 2 to 3, 3 to 4 blind and buried wires, the laser drill, and then 4 to 13, it is a mechanical drill, which is of 6 mil hole minimum. Then after that again blind and buried wires, which is following and going up to bottom layer. So then this is how we reached from top layer to bottom layer using a stacked structure, and then it was connected on the bottom capacitors over here. So that is how it was planned. And then this is with respect to the power, all the power routing. So power routing, as you can see, all the both the layers are over here. Power, which is layer 13 and 14, which is which was kept down so that it is closer to your bottom layer because all your capacitors are on the bottom layer. So we had kept layer 13 and 14. It is also sandwiched between two grounds. So so that it is away from all this high frequency signal layers, and also it is close to bottom layer because all the capacitors are on the bottom layer. So that was the idea behind placing a power over here. Now coming to the actual routing. So coming to layer 7. Now the basic question that would come to my mind is, why did I use layer 7, 9 and 11 for high frequency traces? Why not on the top itself, layer 3 and 5, because it will be closer to your pads. The reason was simple. Um, Layer 3, the references due to the references were not proper, as you can see over here. So we wanted references on both sides. As you can see, the references are getting cut off over here due to the fan outs, because a lot of fan outs was going on layer 3 and layer 5, because all the signals that is coming through, which is going up to 9, 7 and 7, 9 and 11 also will go through 3 and 5. So that's definitely there will be a lot of signal cuts in grounds, and the reference might not be clear because and the 70 ohm lines, they were very critical, so reference had to be very tightly followed. So that was the reason layer 5 and 9, 3 was not used. So we used layer 7, layer 7, right? Yeah, with copper on both the sides. So now here we have tightly followed the reference for layer 7. Similarly for layer 9 over here, and for layer 11. So I'll just hide this. So this. So now again the same strategy we followed. So on layer 9 we used all the signals which are going on top and bottom BGAs so that they don't intersect with one another. And on layer 9 and 7, because of the space constraints, we divided into two halves. So some traces were routed on layer 9 and some traces were routed on layer 7. And we did the length matching with the constraint of 2100 mil. So we successfully did it. But there is a it didn't happen so easily, because now I'll just show you layer 7. I'll show you over here. As you can see, the wire placement over here, they are not very neat. They are not in a structured manner, not in one single line. They are quite jumbled and random. What we do initially, what we try to do is, when we fan out, we try to keep the wires in one line. Like you can see over here, we try to keep in one line, as you can see over here, like this. So initially we had done that, but the problem that was occurring was we pulled it out But since we are pulling it out like this to keep them in one line, the length was increasing, and then going back on the right hand side, going to left hand side and the right hand side, the length was increasing, and that was not meeting our requirement of maximum length. So then we had to do was use whatever space is available, try to push the wires wherever the space is available, and try to reduce the length of the trace as much as possible so that the constraint can be met. So that's why the wires look bit jumbled over here. So so this entire work, not just this much, the entire board, it was on very tight deadline. Within a month we had to do everything. This is just a short section that I have shown you. There was a lot of other circuits over here, the current sensors, then the differential pairs, HPI lines. It was going all around the places. So, and we had to complete this in 1 month, so, and which we did successfully, and the board also worked in one go. So this was a very skillful project, and I'm proud that I was a part of this. So hopefully I have given you good information of what we generally do here at Sierra Circuits. And yeah, so hopefully it will be helpful for you guys and whatever information that I gave you. Thank you.
Thank you very much, Abhishek. So these are some of the resources that we have used for our webinar, and you can check out these blogs. You can get in touch with our CRO, Amit. Feel free to reach out. We also have various design tools and resources that you can check out at our website. We also have a Sierra Network forum, so you can post your questions over there, and our expert will answer them as soon as they can. We also offer end-to-end PCB manufacturing services. Here's what we bring to the table. You can also explore our design services if you need assistance with your PCB design. That brings us to the end of the presentation. Feel free to ask any questions you may have.